Okay, so we're looking at today limit comparison test and direct comparison test. But before we begin that, let us just recap what we've already learned. When we are testing for divergence or convergence, the first thing we want to use is the nth term test for divergence. It's quick and it's dirty, and it'll tell us if a series diverges quickly. So if the limit is 0, it does not tell us that it converges. It only tells us that we have to use another step. If the limit is something other than 0, then we know that it diverges and we can stop. So it's just a very quick test. So if I use the nth term test and it's inconclusive and I have to use another test, the next test I want to try is geometric. And I want to see if it's in this form. And what I know is that if the absolute value of r is less than 1, it converges. If the absolute value of r is greater than 1, it diverges. If it's not geometric, let's look to see if it is a p-series. Now remember, with the p-series, we have the variable n raised to a power. And a p-series, it will diverge if p is between 0 and 1 and converge if p is greater than 1. Then our next choice would be to see if it's telescopic. If it's not geometric, if it's not p, is it telescopic? And at this point in our career, then our next test would be integral test. But we're about to learn two tests that we would do before the integral test, and that is direct comparison and limit comparison test. The direct comparison test is a sweet little test that will quickly tell you if something diverges or converges if you have the right conditions. And the right conditions is this: in order to prove that a function converges, I have to prove that it is smaller than a known convergent series. And the known convergent series that I'm going to look for are like p-series or geometric, things that I can look at and determine if they're converge or diverge easily. So I'm going to compare it with one of those, either p-series or geometric. If it's smaller than a known divergent p-series or geometric series, then a sub n would also converge. So in other words, if the larger series converges, then the smaller series would also converge. The opposite is true. If a sub n, I know a sub n is smaller than b sub n, and I know that a sub n diverges, then the larger one must diverge as well. And this can only work when the terms are non-negative, as you will see. All right, let's look at it. Oh, we have one more thing. This is just a visual to show you what we're talking about. So the red is a known convergent series. If the blue series is smaller, consistently smaller than the red, then we know that the blue series would also converge. And here we're showing that the blue series is a known divergent series, and if the red series is smaller, then it would also diverge. I'm sorry. The red, I said that wrong. The red is the smaller one, and it diverges. Then the blue has to diverge as well. Okay, let's do this example. We have this series 1 over n squared plus 1. So what we have to ask ourselves is, what does it look like? What does it resemble? And you may see that it sort of looks like 1 over n squared. 1 over n squared is a p-series where p is equal to, and therefore it converges. So 1 over n squared converges. In order for me to prove that 1 over n squared plus 1 converge, I have to prove that it is smaller than n squared, 1 over n squared. Okay? So you may be able to look at that and tell that just by looking at it, but if not, you can also say, okay, I need 1 over n squared plus 1 to be less than 1 over n squared. Okay? So I need to see if 1 over n squared plus 1 is less than 1 over n squared, and I can do that by cross multiplying. I get n squared is less than n squared plus 1, which this is a true statement. So therefore, I know that 1 over n squared plus 1 is smaller than 1 over n squared, and therefore this 1 over n squared plus 1 converges. Okay? Let's do another example. Okay, so again, I want to know, what does this look like? So this looks like 1 over n to the 2/3. That's what that resembles. And I know 1 over n to the 2/3 is a p-series where p is equal to, and therefore, because p is equal to 2/3, this diverges. So in order to prove that this entire thing diverges, I would have to prove that 1 over the cube root, well, I'm just going to write it, well, I got to write it, the cube root of n squared minus 2. I have to prove that that is greater than 1 over the cube root of n squared. Okay? I have to prove that this is greater. Once again, because I'm subtracting 2, that's going to make this denominator larger, and it's going to make the whole thing smaller. But let's just, because I'm subtracting 2, it's going to make the denominator smaller and the whole thing larger. But let's just look at it algebraically for a second. So that means I'm going to have the cube root of n squared is greater than, as I cross multiply, the cube root of n squared minus 2. And we can see that that's true, because if I'm subtracting 2 from this term will be greater because I'm subtracting 2 from it. So since this is larger than its known divergent component, we can say that this diverges. Okay? All right. Again, we have to look at, what does this look like? And all of these examples are on page 8. I hope you're keeping up with me. These are on page 8 of your notes. All of these, so we have to look at, what does this look like? And this looks like 1 over n cubed. Now, what do I know about cosine squared n? Cosine squared n is going to be between, these values are going to oscillate between 0 and 1. Because I'm squaring it, therefore it's always going to be positive, but it's going to be between 0 and 1. So essentially, it's going to be a fraction. So since I'm multiplying this by a fraction, I can say that it's going to be less than 1 over n cubed. And since 1 over n cubed converges, and this is smaller than 1 over n cubed, I will also say that this converge. So if you didn't like the way that I reasoned that, let's do it this way. I have to prove that this term is smaller than this term, so I'm going to cross multiply again. Get n to the cube, cosine squared n is less than n cubed plus 1. So once again, because this is a fraction, it's going to make n cubed smaller than adding 1 to n cubed. And so since it's smaller and 1 over n cubed converge, the entire thing converges. All right, let's use direct comparison on the following. And we're just going to kind of take this slowly. All righty. So the first one is a little different because I kind of need to know what approximate the natural log of 2. Natural log of 2 approximate to approximately 6 point something, 0.6 something. And so since I know that that approximates to 0.6 something, then I know that actually by the nth term test, I can go ahead and see that that's going to diverge by the nth term test, because essentially what I have is 1 over 0.693 to the nth power. But because, well, more like this, 0.693 raised to the nth power. But I have 1 divided by a small number, which makes this entire thing big, and so this actually fails the nth term test. It also fails the geometric test, so this will diverge by the nth term test. Okay? So the natural log of n plus 1, that one is, for some reason, is not in your notes, so we'll come back to that one. This one looks like 3/4 to the n. And we know by geometric series that 3/4 to the n will converge because it's geometric. So what I have to prove is that 3 to the nth, 4 to the nth plus 5, I have to prove that that is smaller than 3 to the nth over 4 to the nth. Okay? Because I know 3 to the nth over 4 to the nth converges, I have to prove that this is smaller. So I do that by cross multiplying. I get 3 to the nth, 4 to the nth, and is that smaller than 3 to the nth, 4 to the nth, plus 3 to the nth plus times 5, using distributive property. So, of course, 3 to the nth, 4 to the nth is smaller, so I've just proved that this converges. Okay? The second one, it looks sort of like 1 over the square root of n. So 1 over the square root of n does what? It diverges. Why? It's a p-series where p is equal to 1/2. So it diverges by p-series, 1 over n. So in order for me to prove that this diverge, I have to prove that it is greater than 1 over n. So I have to say 1 over 2 plus radical n is greater than 1 over radical n. So I get n is greater than 2 plus radical n. Now, is that a true statement? Is n greater than 2 plus radical, I'm sorry, this would be radical n, sorry. Radical n is greater than 2 plus radical n. Well, that's not a true statement. So since I could not prove that this series is greater than this series, since I could not prove that, then I have to say that the direct comparison test is inconclusive, and I would have to use a different test. It's inconclusive. I would have to use a different test. Okay? All righty. Let's go back to this one. What does this look like? Probably 1 over n. And we know 1 over n does what? It's a harmonic series. It diverges very slowly. We learned that in the other video. So this diverges. So once again, I have to prove that the natural log of n over n plus 1 is greater than 1 over n. I said greater than and wrote less than. Okay? So I have n, natural log of n plus n plus 1. Now, when a certain values, n, or natural log of n is going to be fractions. However, when I get to like the natural log of e and above, this becomes a whole number. So remember, we're looking at what's going on as we go towards infinity. So as we go towards infinity, the natural log of the earlier values, this may not be true. But for later values, as we go towards infinity, this is true. The n times the natural log of n would be greater than n plus 1. So I could also prove that this diverges as well. Okie dokie? Okay. So that's it for direct comparison. And watch the second video on limit comparison.